So hi, today we will talk about the equivalent circuit of induction machines. So as we discussed in the last week, so as the rotor speed changes, the frequency of the currents induced in the rotor bars are also changing. And assume a condition where the rotor is stationary. So in this case, remember the slip is 1, so S is equal to 1. So when the rotor is not rotating, then the frequency of the rotor bars can be expressed as, they are written as like SFS, and when S is equal to 1, so the rotor bar frequencies are equal to stator frequency. So if you have a, for example, 50 Hertz induction machine, and somehow if you just keep the rotor stationary, you can lock the rotor, and the frequency at that condition will be the rotor bar's current frequency will be also 50 Hertz. So actually at that condition, if you look to the motor, so you apply some AC voltage to the stator windings, and it induces some AC currents at the rotor bars or rotor winding. So it just becomes like a transformer. Okay, so the condition is, so we don't have any like in a transformer, we don't have any terminals to connect an external load. So the induction motors, in a squirrel cage induction motor, remember the rotor windings are short-circuited, so it is like a short-circuited transformer, and our stator winding is actually equivalent to the primer winding of the transformer, and our rotor bars are equivalent to secondary winding of the transformer, which is short-circuited in our case. So in that case, you can represent, just to remember the equivalent circuit of a transformer from the first semester. So remember, we have R1 and X1, and R1 was in the transformer, it was the resistance of the windings that were used, right? So you can call them like stator winding resistance. Okay, and similarly X1, normally in a transformer, it was the inductance or reactance of the primary winding. Okay, in our case it is the stator winding. And we have, again, we will talk more detail, but we have X2, R2. Again, if you just put those like that, then they represent the actual values of the transformers. But again, from electrical point of view, they're not really useful. So what we want to get is the referred values of those parameters. So remember, those shows the referred rotor parameters. Similarly, R2 is the resistance of the rotor windings, X2 is the inductance of the rotor winding. And we have an XM, so because we have the magnetic core, and actually XM becomes more important in an induction machine, because normally in a transformer we have a high permeability core. We don't need any air gap or something like that. So actually in an induction machine, if you think about it, that you have to have like really small air gap, but that small air gap has a low permeability compared to the permeability of the electrical steel, the main core material. So therefore you have a higher reluctance compared to transformers. So XM usually is smaller. So XM being smaller means you will have a larger magnetizing current. Okay, so this is, remember, the magnetizing inductance. Okay, so if you have any problems remembering those equivalent circuits, I strongly advise you to go back to your notes from the first semester, because we will be using that transformer equivalent circuit for the induction machines. Okay, so this is the case when the rotor is stationary, so you can say the rotor current frequency is again 50 Hz, so we have 50 Hz. Again, you can refer those things, remember, with respect to induced voltage magnitudes or number of turns. And again, if you think the induction machine rotor bars are short-circuited, so it is like having a number of turns of 1, but actually we don't get into those details much in this course. Anyway, so now assume the rotor now start rotating. Okay, so when it was stationary, the rotor currents frequency was 50 Hz. Now it starts rotating. So remember, as it starts rotating, the actual difference between frequencies gets smaller. For example, forget about the number of poles and that kind of things to simplify things, or assume it's a two-pole machine. So assume we have a 50 Hertz excitation, 50 Hertz voltage and currents at the stator, and the rotor is rotating at 10 Hertz. Okay, mechanically it's rotating at 10 Hertz. So the induced voltages, the induced MMF, will see the stator MMF as if like it's going at 40 Hertz. Okay, remember, like two trains, you are looking at the other train and you see the other train with difference of these two trains. So that's the same logic. So when it is rotating at 10 Hertz, the current's frequency drops to 40 Hertz. If it speeds up to, I don't know, 20 Hertz mechanically, then the rotor frequency drops to 30 Hertz, and goes so on. And for example, if the rotor starts rotating at 45 Hertz, okay, then you have 50 Hertz stator excitation still. So the difference just becomes to 5 Hertz. So the frequency of the rotor bars, rotor currents reduces. Okay, so therefore, remember from first semester, E is again proportional with the frequency of the, or rate of change of the flux. Okay, so as the frequency reduces, the rotor induced voltage also reduces. So normally, the magnitude reduces, the voltage magnitude reduces, the current also reduces, but not as linearly as you expect. If you have just the resistive load, then yes, if you halve the voltage magnitude, then the current will be half. Okay, but what we have is, we also have, here we have the resistance of the rotor bars. Okay, and we have the inductance of the rotor bar. So you are say applying some voltage. Okay, that's not E. So the magnitude also changes, but the frequency also drops. Okay, so if you halve the frequency as the rotor increases, rotor speed increases, the magnitude will be half. But as the frequency drops, okay, that component will also drop. So that will not cause a linear relation, but it's kind of a, we will derive those equations in the following videos, but there will be some nonlinear change with the current. But at the end of the day, what can I represent the rotor as a RL load, and I need to find a way to transfer that rotor circuit back into the stator. Again, I'm not getting into much detail of the derivation of those transfer. You can check your textbooks or other, I will put some PDF files as well. So if you just look at the stator side equivalent circuit, again, it is more detailed one that with the one I first showed. So here, this is a proper circuit where we have the R1, X1 as well, and we have RC. Normally RC is not as dominant as in the transformers, but XM can be dominant. And RC, remember, it represents the core losses. Remember the hysteresis and eddy current losses in the BH characteristics of the core material. So we have Xm. So here that is the like voltage E1. So that is the voltage that is being transferred to the rotor through the air gap. Okay, so this is the stator side, and on that side we will have the rotor side as well. So let's have a look at the rotor side. So I can represent, remember, when the rotor is stationary, was generating at maximum frequency, let's say at 50 hertz. So as it goes down to 5 hertz, then also the voltage, induced voltage magnitude, will be reduced by 10, factor of 10. So from 50 hertz to 5 hertz, voltage magnitude can be reduced by 10. Or somehow, if you just rotate the rotor at the same with the synchronous speed you have seen in the previous video, so what you will see is from the rotor's perspective, it will just see a constant MMF, so there will be no induced voltages, so you will not have any currents induced in the rotor if the rotor is rotating at synchronous speed. So that is really fundamental property of induction machines, and that is the reason why induction machines are called asynchronous machines, because they cannot rotate or they cannot generate any torque at the synchronous speed. So that is the main difference between synchronous and asynchronous machines. Anyway, so because of that, I can represent the magnitude of the induced voltage that couples the rotor circuit as S times E2. Okay, you don't have to worry about the details. I'm happy if you just understand the main logic. So as the slips get bigger, that voltage will get bigger. As the slips get smaller, it will get smaller, and when slip is equal to 0, that will be 0 as well. And we have R2, okay, that is just resistance, okay, and I can write the inductance, okay, as I can write as again normal like J omega L, but that omega is not actually our stator excitation frequency. That omega here is the rotor current's frequency. If it is 5 hertz, it will be 2 pi 5, so 10 pi, or if it is like 50 hertz, like in the Locked-rotor case, it will be 2 pi times 50 hertz. Okay, so that is changing. So I don't want to deal with that changing frequency. So I can represent that frequency as a function of the stator frequency and the slip. Okay, so that F1 here is the main stator excitation frequency. In our case, let's say it's 50 hertz. Then I can write that inductance as S times or 2 pi SF1. SF1 is equal to rotor frequency, so times L is the inductance, so it is Sx2. So now that is okay, but I want to link that one to the stator side. So instead of writing a variable voltage like SE2, I can modify it like the circuit on the right hand side. Again, I'm not getting into much details, but I will upload some notes about the derivation of that circuit. But briefly, so when you can calculate the power relations, whatever, again, remember the Thevenin equivalent circuits, Norton equivalent circuits, you can simplify the circuits as if they have the same characteristics. So what I am doing is I'm dividing the voltage by slip. Okay, if I'm divided by slip, then E2 becomes SE2 becomes E2. Then S times 2 pi F1 L2 divided by S cancels out, so you have X2, okay, and X2 is equal to 2 pi F1 times L2, and F1 is the stator frequency. So I just got rid of the slip component here. But if you just keep the rotor constant, constant, then you will end up with not constant power. So I'm dividing my R2 by S in order to have the same relations. Again, the derivation will be available, and I'm not getting into details in this video. So we have E2, X2, and R2 over S. So now, I can connect that rotor side as if, it is a transformer. So I just, not transformed my circuit with, number of turns, but also I transformed my circuit with respect to frequency. So again, at the end of the day, I'm not really interested in what is the actual magnitude of the rotor currents. What I'm more interested is what is the reflected effects on the stator. So at the end of the day, I can't measure any rotor currents or voltages. They are rotating. There are no terminals that is coming to the outside. I can measure the stator phase voltages and currents. So I would like to see those effects as seen on the stator windings. So that is, our circuit. So that is the equivalent circuit of the induction machines. So here again, that parallel branch is actually here in a more appropriate circuit, but it can be simplified. It can be moved to the primary terminals, like we did with the transformers as well. And RC is the core resistance, XM is the magnetizing reactance, R1 and X1 is the stator winding components. So now I have the X2 prime, actually that is the referred rotor reactance, and I have R2 prime over S. Okay, so don't forget that S component, R2 is actually the real resistance, but R2 prime S is the referred resistance primary. Okay, so again, the current here can be again like the transformer. It can be written as I2 prime. Prime is for the referred, and PAG here is air gap power. Okay, air gap power. So actually that side is our stator. Okay, that side is our rotor. Okay, so the power, we will use that power in the following videos. So you just calculate how much power that is going over from that dash line, that boundary. That also shows us how much power is transferred from stator side to rotor side. Okay, and if you think about it, there will be some losses. We will talk about those things in the following videos, but for example, you will have I square R1 losses here, which is the heat generated on the stator windings, the copper windings of the stator side, and you will have V1 square divided by RC. So these will be the core losses. So these are the loss component that heats the core material in the machine. And again, you can calculate the I2 prime squared times R2 prime divided by S, and we will see some of that power actually heating the rotor bars, but actually we will see some of that power is also transferred to the mechanical system. Anyway, for now, please get familiar with that equivalent circuit, and actually I will give you a couple of numerical examples as well. So let's discuss how we can generate, or how we can estimate or measure those equivalent circuits. So if there is not an actual way of connecting multimeter to the rotor, so how can I estimate the R2 component or X2 component? Okay, so for that, please remember the two tests that we used for transformers, and those were the open circuit test and short circuit test. So briefly, what we were doing is we were just disconnecting the load from the transformer, which is the open circuit test, and you are applying some rated voltage and you are measuring the loss component, so you can find the parallel branch components. And what you were doing is you were short circuiting the secondary side, okay, then applying a small voltage, and with that one you are trying to estimate the equivalent circuit parameters of the series branch. So we will have the same logic here. So instead of no load test, open circuit test, we will have no load test, which you just run the electrical motor without any load, nothing connected. So it just runs really close to synchronous speed. And what you do instead of short circuit test is you just lock the rotor, so you don't let the rotor to rotate. Then you apply some tests. So let's get into those details. So first, let's start with the Locked-rotor test. Okay, so in that one, rotor is kept stationary with a mechanical locking system, so you can just it cannot just rotate. So in normal, we had those experiments in our labs, but you will do a homework and also some simulation experiments this semester. So our rotor speed, okay, RPM or whatever, radian per seconds, so that is 0 if the rotor is not rotating. My slip is equal to 1. Okay, then under that condition, I mean, if you apply rated voltage, you remember damage your transformer, and similarly it can be harmful for your induction machines. So you apply a small voltage, usually like 10-15% of the rated voltage, to obtain rated current. And you measure the input power, input voltage, and current. Okay, so by using those calculations, again, I will solve a numerical example, but you will be able to estimate the series circuit parameters. So what happens? Okay, let's go back again. This was our equivalent circuit, and in the Locked-rotor test, so S is equal to 1. So you have that voltage, and you are applying a really small voltage, 10% of your rated voltage, for example. Then that parallel branch currents becomes really small, and again at the end of the day, like this can be like a couple of ohms or milliohms, maybe those series circuit components, but those parallel circuit components are usually in the kilo ohms range, or maybe 100 ohms. So that current is usually smaller component compared to that one, and if you apply a small voltage, that becomes even smaller. So that was the reason why we can ignore the parallel branch. Okay, so if you ignore the parallel branch, and the circuit becomes like that. Okay, so by measuring the voltage and current, you can try to estimate those components. And actually another really important thing, I think it should be obvious, but let me repeat, all those components that we have seen are per phase equivalent circuit, as in the transformers and as in the synchronous machines. So here I1 and V1 shows the phase voltages and currents, but if you calculate the total power, then you shouldn't be, you should be dividing it by 3 to get the per phase equivalent circuits. Anyway, so in the test, if the total power is given, then you divide it by 3, then you can calculate the per phase power. And the real power dissipation, remember, real power only dissipates through resistances, and we have, let's say, I1 current, so I have I1 square R1 plus R2 prime. So if I know the power, I know the current, I can estimate R1 and R2, total resistance. So what you can do then, I mean, how you are going to, distinguish between R1 and R2 prime. So what you can do is you can actually stop the machine, for example, measure the phase resistance with a multimeter. If you just connect the ohm meter to stator terminals, which you have like 3 cables coming out of your machine, you can measure the stator resistances, but you will not be able to measure the rotor resistances because again visualize the rotor and stator, so they are not electrically connected, so there's an air gap. That was the main advantage of an induction machine, but there are no brushes, nothing to connect electrically to the rotor. All the power is transferred wirelessly. Okay, so you can calculate the R1 and then you can estimate the R2 prime. Then you can divide V1 and I2 to calculate the equivalent impedance, and you already know R1 and R2, so you can get X1 and X2 prime. And actually there are some methods to estimate X1 and X2 prime, but usually they are really close to each other, and even if they don't, at the end of the day they are just two impedances connected to the same line. So we don't really, if you are not really interested in what's happening between stator and rotor, the easiest way is to just assume X1 is equal to X2 prime, so you can get calculations. Okay, so the next test we need to apply to get the remaining circuit parameters is the no load test. So it is like the open circuit test in a transformer. So you just disconnect all the loads to the mechanical loads to the induction machine, and you let it run at no load. And if there is no mechanical torque, yes, we have some frictions, but can be negligible. So the rotor speed increases, just generates some torque. For example, if the stator excitation frequency is 50 Hz, you can start from 0 Hz rotor. It quickly accelerates 10 Hz, 20 Hz, 30 Hz, 40 Hz, 45 Hz, 46 Hz, but at 45 Hz there are still some current rotating at 5 Hz in the rotor, and that still generates some torque. So it just keeps increasing, 49 Hz, 49.1 Hz, 49.5 Hz. So it becomes like, technically it cannot run ideally at synchronous speed because of some friction losses, but it can come really close to the synchronous speed, and that condition we can get zero slip, or we can assume the slip is zero. So if the slip is zero, okay, again let's go back to our original circuit. If the slip is zero, then that means our rotor bars like open circuited and I2 prime becomes zero. So that is reasonable. And actually if you think about the actual case, as the rotor becomes close to synchronous speed, from the rotor's perspective it is like a constant MMF, so there will be no voltages, there will be no currents, so it becomes like open circuit, and our equivalent circuit shows it by that component R2 prime over S. As slip goes to zero, that resistance goes to infinite, and that branch becomes open circuit. Normally that thing is here, yes, but again we can make some assumption and move it to the primary winding, and that all that component, actually I think I have the same circuit here. Okay, so let me write here, so S is equal 0, so that one open circuited, so that one cancels, and I2 prime is equal 0. So we have just that part, so that is the no load equivalent circuit. So in this condition, if you measure again V1, I1 and total power, then you can calculate the equivalent parameters of that parallel branch. I mean, it's technically same with the transformer open circuit. Again, you can calculate the phase power by dividing the total power by 3, and power, real power, only dissipates at resistive components. So you can write V1 square over RC is equal to that one. So you can find RC, and you can divide V1 and I1 to calculate equivalent impedance. And once they are in parallel, so you can calculate the value of X. Okay. And for again mechanical, friction and windage losses are always there. So slip is not ideally 0. It's a really small number, but it should be larger than 0. So what you can do is, actually you can get in actual cases, they do in factories or in experiments as well. So you can run the motor at different voltages and different frequencies. It causes different speeds. So you can get an understanding of how the frictions are changes, or if you know the geometry and if you know the brands of the bearings, you can also estimate the friction and other mechanical losses. Okay, so let's stop here, and I will solve that video I will solve that problem in the next video.